Hello and welcome, aspirants, to today's Rungta IAS Academy Explainer. We're diving straight into your GS Paper 3 Science and Technology syllabus today, decoding a genuinely fascinating nature physics study on programmable metamaterials. Now, this was recently reported by Vasudevan Mukund, that's pronounced Vasudevan Mukund, in The Hindu. It's a brilliant topic and absolutely crucial for your mains preparation.
Exactly, sir. So, aspirants, grab your notebooks. Our note-making structure today is going to rigorously cover 5 key dimensions. We'll look at the GS3 context, defining metamaterials, contrastive learning, non-reciprocity, and bistability. And finally, we'll wrap up with your exam strategy. Let's get right into it.
All right, starting off with Dimension 1, the GS3 context.
You see, the core problem we're looking at here is adaptation. Think about nature, right? Biological materials adapt effortlessly. Our muscles get stronger when we lift weights. Plants literally bend toward the sunlight. But traditional, non-living materials, they're completely static. Once you forge a steel bar, its internal structure is pretty much fixed for good. Well, this new European study essentially bridges that exact gap between the living and the non-living.
Moving to our second dimension, defining programmable metamaterials.
Now, aspirants, I want you to note this down verbatim for your mains answers. A metamaterial is a special material whose properties are determined not just by its chemical composition, but fundamentally by its physical structure. This unique physical arrangement is what gives it highly unusual traits, things like bending light or even shielding against earthquakes. So, underline this, the absolute focal keyword here is physical structure.
Take a look at this. What you're seeing here is visual proof of a robotic metamaterial chain physically morphing step by step to spell the word learn. It's quite incredible. It's essentially a chain of connected units, and within each individual unit, you have a small motor, an angle sensor, and a microcontroller all working together.
Which brings us to our third dimension, hardware-based contrastive learning.
So, how does this non-living material actually learn without a centralized brain? Well, it relies on local decision-making, and it happens in 4 steps. First, we have the straight line phase, where the chain starts completely straight with a set starting stiffness.
Right. And second is the free state. If you bend just one unit, it pushes the entire chain into a new shape.
Then comes the third step, the clamped state. This is where researchers manually force the chain into a specific shape, like a U or an L.
And fourth, the stiffness adjustment. The local microcontroller actually compares these different states and adjusts the stiffness accordingly. This is learning purely through hardware, totally bypassing those complex machine learning backpropagation networks we usually see in AI.
Now, you might be wondering, how do you scale this up? The researchers hit a bit of a technical hurdle here: signal decay over long chains. To build larger, more complex shapes, say a 48-unit outline of a cat, these units had to communicate better. So they successfully expanded this local communication. Now each unit talks not just to its immediate neighbor, but also to the next nearest unit, 2 steps away. That simple change allowed the inputs to propagate much further down the line without decaying.
Let's move to Dimension 4, non-reciprocity and bistability. 2 absolutely vital vocabulary words that will fetch you extra marks in the exam.
Definitely underline non-reciprocity in your notes. Traditional physics tells us that a spring learns by finding its lowest energy state, or its valley. But Dr. Karen Allam's commentary points out that this metamaterial challenges that completely. It's non-reciprocal. Push it from the left, and the right side bends one way. But push it from the right, and the left side bends completely differently. It essentially learns by minimizing physical work along very specific paths.
And then we have bistability. Imagine these units acting like little switches that can transition between stable states. Think about it like a reflex action. If an object touches the chain, it automatically coils around to grip it. Give one unit a slight nudge, and the whole thing uncoils. These are incredibly lifelike actions happening in a purely mechanical material.
Finally, bringing it all together with our most important phase, Dimension 5, your mains and interview strategy. Now, realistically, this technology currently relies on things like airtables and rather impractically large components in the lab. But once we overcome these limitations, the potential real-world application is just vast. We are looking at a future with advanced prosthetic limbs that actively adapt to a user's movements, or soft robotics that can agilely navigate around unpredictable obstacles. It is going to be a real game-changer for adaptive physical systems.
Absolutely. So, to consolidate all this learning, here is a highly probable mains practice question for you to tackle.
Evaluate the role of programmable metamaterials in blurring the lines between biological adaptation and physical mechanics. Discuss potential applications in robotics. I want you all to structure an answer in the comments below, making sure to use the exact keywords we discussed today. Keep revising diligently, aspirants, and we'll see you in the next Rungta IAS Academy Explainer.